This is a very exciting time for AI. In some domains, the accuracy of AI algorithms has surpassed that of humans, a fact that is well known by society as a whole, not just in the research community. However, most of the high-performing AI algorithms work as black boxes. The data is fed to the algorithm, and the algorithm provides highly accurate output, but there are no clues or answers as to what these outputs are based on. In many applications, this knowledge is very valuable. The tool I'm about to demonstrate provides the end user with an informative dashboard, which allows to pick the samples you want to evaluate, pick the model you want to understand, and then choose one of many XAI methods to use. The component then displays the results of the XAI algorithms directly to the user. Here you can see the high-level architecture of the component. We start with the user, who, after authentication, can see the dashboard and issue requests. The tool uses a publish-subscribe bus to move samples around the different microservices. The tool uses AI model integration interfaces, which handle communication with the different AI models used in the project. Then, there are different data pre-processing services, which handle the transformation of data to be fit to use in different algorithms. Then, we have different XAI microservices. Since some of the XAI algorithms are computationally demanding, we have built ways to save the results of the analyses into data storage, so the user does not have to wait for the same explanations to be computed multiple times. This is a demonstration of the AI4CYBER explainability component developed in Task 6.1. We start with the view of the ITTI's internal network intrusion detection component. The component features a machine learning detector trained on the LitNet benchmark dataset. After clicking Explain, the sample is forwarded to the XAI component, where the particular explanation method can be chosen from a range of listed options. A range of XAI methods is available to allow both local and global explanations. The methods include local interpretable model agnostic explanations, LIME, Shapley additive explanations, SHAP, diverse counterfactual explanations, DICE, scoped rules anchors, partial dependence plots, PDP, individual conditional expectation, ICE, plots, and more. Currently, you can see a plot of feature importances attributed by LIME. LIME generates a new dataset consisting of perturbed samples around the instance being explained and obtains predictions for these samples from the complex model. It then uses these new samples to train a simpler model. This simpler model is interpretable and can be analyzed to understand which features influenced the prediction for the specific instance. The next explainer is the tree-based Oracle explainer developed by ITTI. The algorithm ingests the sample along with the classification performed by the Oracle AI and compares them with pre-trained explanation clusters in search of the closest match. A decision tree linked to the closest cluster is used to explain the Oracle's prediction. This explainer module is flexible and model agnostic. The DICE, diverse counterfactual explanations, explainer generates counterfactuals, hypothetical scenarios showing what minimal changes would be needed for a different prediction outcome. DICE focuses on diversity, ensuring the counterfactuals it produces are varied but plausible. The process involves tweaking input features of a data instance and observing how these changes affect the model's prediction. These changes are presented as if-then scenarios, helping in understanding the model's decision-making process. In the explainer module, you can see both the original sample and a set of 5 feasible counterfactual examples. The anchors explainer identifies anchors, explanations in the form of rules, which are specific conditions that, when satisfied, predict the same outcome with high probability. Anchors offer insights into what factors are most influential in a model's decision-making process. The explainer tests various feature combinations from a data instance to identify which conditions consistently lead to the same prediction. Anchors is model agnostic. SHAP, Shapley additive explanations, assigns an importance value to each feature. showing how much each one contributes to the final prediction. SHAP is based on game theory, particularly the Shapley values concept, which ensures fair attribution of contributions among features. It's model agnostic. PDP, partial dependence plot, is a visualization tool used to show the relationship between a feature and the predicted outcome. It illustrates how changes in a feature affect the model's predictions on average over a data set. PDP helps in understanding the global effect of a single feature, ignoring interactions with other features. It's useful for interpreting complex models by providing a straightforward graphical representation of feature influence on predictions. ICE, individual conditional expectation. Plots display the change in prediction for each individual instance when a feature is varied. This allows for the observation of how predictions change for specific data points, revealing interactions and heterogeneity in the model's behavior. A dashboard combining ICE plots and PDP plots provides a comprehensive view of how a feature influences predictions, both on average and for individual instances, highlighting potential variations or anomalies that might be overlooked when considering only the average effect. ALE plots, accumulated local effects, compute the model's predictions for data points within intervals of a particular feature. These local effects are then added up over the intervals, starting from one end of the feature range to the other. This provides a realistic picture of how changes in a feature influence predictions. Permutation feature importance. PFI is a straightforward model-agnostic approach that directly measures the impact of each feature on the model's performance by shuffling its values. PFI disrupts each feature and observes the change in accuracy, which makes it widely applicable and easy to understand, offering clear insights into feature relevance irrespective of the underlying model structure. RuleFit generates a set of rules from decision trees and combines them with linear models. The final model is a linear combination of these rules and original features, making predictions based on both. The method outputs in the form of rules and weights, making it more interpretable than many black box models. It provides insights not just into which features are important, but also into how different feature combinations affect the outcome.